There is a river moving through the Atlantic, wider than nations and deeper than any valley carved by rain. It has no banks, no visible shore, no single surface that a person can stand beside and watch. It moves through temperature, salt, density, wind, and gravity. It carries warm water northward, sends colder water back south at depth, and helps regulate the climate of continents that rarely think of themselves as oceanic. Scientists call this system the Atlantic Meridional Overturning Circulation, often shortened to AMOC. But for the rest of this story, it is easier to think of it as the Atlantic's hidden engine. Warm surface water moves north through the Atlantic. In high latitudes, the water cools, becomes denser, and sinks. Then it returns southward in the deep ocean, part of a vast overturning movement that links the surface to the abyss. The danger is simple to state and difficult to measure with certainty. If this circulation weakens enough, the consequences could spread far beyond the Atlantic. Weather patterns could shift, rainfall belts could move, sea level could rise faster along parts of the North American coast, marine ecosystems could change. Europe could face altered winters even inside a warming world. A current hidden beneath waves could change the lives of people who never see the ocean. This Atlantic circulation depends partly on density. Warm water is usually lighter than cold water. Fresh water is lighter than salty water. In the North Atlantic, water carried northward loses heat to the atmosphere, becomes colder, grows denser, and can sink into deeper layers. This sinking helps pull more water northward behind it, maintaining a circulation that transfers heat across the basin. The system is more complex than a simple conveyor belt. Winds matter. Seafloor shape matters. Mixing matters. The Southern Ocean matters. Ice melt, rainfall, evaporation, and salinity all influence the balance. The circulation is not one neat ribbon of water moving at one speed. It is a basin-wide pattern of surface and deep flows with branches, feedbacks, and regions where small changes can matter. The phrase current can make the system sound smaller than it is. The Atlantic's hidden engine is a moving architecture inside the ocean. It helps distribute heat, carbon, oxygen, and nutrients. It connects tropical waters with polar seas and surface conditions with deep storage. It is one of the reasons the Atlantic climate has the shape we know, and one of the reasons scientists monitor the North Atlantic so carefully. Western and Northern Europe are strongly influenced by the Atlantic. Warm water transported northward releases heat into the atmosphere, and prevailing winds help carry that influence toward the continent. This does not mean Europe is warm only because of one current. The climate system is more layered than that. Yet, the Atlantic heat transport is important, especially for the contrast between European winters and winters at similar latitudes elsewhere. A weakening of this Atlantic circulation could reduce northward heat transport. The result would not be a simple ice age, because greenhouse warming continues to add heat to the planet. Instead, regional climate patterns could become more complicated. Some areas could experience cooling influences against a warmer global background. Storm tracks could shift. Rainfall patterns could change. Sea ice, marine ecosystems, agriculture, infrastructure, and energy demand could all be affected in different ways. This is why this hidden circulation attracts public attention. It is one of the rare ocean systems whose name has entered climate conversations beyond science. People sense that it touches something fundamental. A hidden circulation in the Atlantic helps shape the weather of nations, and the possibility of weakening turns the ocean from background into actor. One of the central concerns is fresh water entering the North Atlantic. As Greenland melts and Arctic changes accelerate, more fresh water can enter regions where dense water formation is important. Fresh water lowers salinity, which can make surface water less dense. If the water does not become dense enough to sink efficiently, the overturning circulation can weaken. This is a delicate process because it involves thresholds and feedbacks. A slower circulation may transport less salty water northward. Less salt can further reduce density. Less sinking can weaken the pull of the circulation. Scientists study these mechanisms through observations, climate models, ocean moorings, sediment records, and reconstructions of past climate shifts. The challenge is uncertainty. This vast current system is difficult to measure over long timescales because continuous direct observations are relatively recent. The ocean has natural variability, and human-driven climate change is now imposed on top of that variability. The result is a scientific problem where the stakes are high, the system is complex, and the exact timing of future change remains debated. Observations and research have raised concern that this Atlantic circulation is weakened in recent decades, though scientists continue to debate the size, causes, and future path of that weakening. Direct measurement arrays across the Atlantic have provided valuable data, while indirect evidence from temperature patterns, salinity, ocean records, and models adds broader context. The North Atlantic has shown patterns consistent with circulation change, including a region of unusual cooling sometimes discussed in relation to reduced heat transport. The problem is that this circulation cannot be judged from one measurement alone. It varies by season, decade, region, and depth. Short-term changes can be large. Long-term trends require careful analysis. Climate models do not all agree on the exact pace of future weakening, and some processes, such as Greenland meltwater or small-scale ocean mixing, are difficult to represent perfectly. Still, the concern is serious. Recent scientific work has continued to emphasize that the overturning circulation is vulnerable to warming, freshwater input, and changes in the high-latitude Atlantic. The question is no longer whether this Atlantic engine matters. The question is how much it will weaken, how quickly, and whether the system could approach a tipping point under continued warming. A tipping point is a threshold where a system shifts into a different state and does not easily return. For this Atlantic circulation, the feared scenario is a collapse or severe weakening of overturning circulation. This would unfold over time, rather than as a cinematic instant. Yet once the system passes a critical threshold, recovery could be extremely difficult on human timescales. The idea is unsettling because it challenges normal expectations of gradual change. Many climate impacts increase in degrees: warmer air, higher seas, stronger heat waves. A circulation collapse belongs to a different category. It would alter patterns of heat movement, rainfall, sea level, and marine productivity through a large-scale reorganization of the ocean. Scientists do not present every model result as destiny. They use models to understand risk, probability, mechanisms, and warning signs. The exact threshold remains uncertain. The possibility itself is enough to matter. A small chance of a severe climate reorganization cannot be treated like an ordinary forecast error. It is a risk attached to one of the planet's major life support systems. A major weakening of this Atlantic circulation could affect Europe, North America, the tropics, and the ocean itself. In Europe, winter conditions could shift as northward heat transport changes. In the tropics, rainfall belts such as the Intertropical Convergence Zone could move, affecting monsoon systems and agriculture. Along the U.S. East Coast, regional sea level could rise because ocean circulation helps shape sea surface height. Marine ecosystems could be disrupted as temperature, oxygen, and nutrient patterns change. The ocean stores and transports carbon. Changes in overturning can affect how carbon moves between atmosphere, surface waters, and the deep sea. Nutrient supply can also change, altering plankton productivity and food webs. Fisheries could shift as species move with temperature and habitat. A circulation change in the Atlantic would therefore be climatic, ecological, economic, and social at the same time. The most important point is connection. A current in the Atlantic can influence rainfall in Africa, storms in the North Atlantic, sea level near American cities, and temperatures across parts of Europe. The ocean makes distant places neighbors. Its currents are not scenery. They are infrastructure created by physics. People often use the Gulf Stream and this larger Atlantic circulation as if they were the same thing. They are related, but the relationship is more precise than the popular phrase suggests. The Gulf Stream is a strong surface current carrying warm water along the eastern coast of North America and into the North Atlantic. The larger Atlantic circulation includes both northward surface flow and southward deep return flow. The Gulf Stream is strongly driven by winds and Earth's rotation, and it would not simply disappear in the same way a fictional switch might turn off. A weakening of the deep Atlantic circulation would affect the broader pattern of Atlantic heat transport and deep circulation. Mixing these ideas can create confusion, especially in dramatic climate storytelling. The real story is strong enough without exaggeration. A major weakening of this hidden circulation would be consequential even if surface currents continued in altered form. The danger lies in reduced overturning, changed heat distribution, freshwater feedbacks, and the movement of climate zones. The ocean does not need to stop like a machine for the world to feel the change. Earth's past contains evidence of abrupt climate shifts linked to ocean circulation changes. During the last ice age and deglaciation, the North Atlantic experienced episodes where freshwater input, ice dynamics, and circulation changes were associated with rapid regional climate shifts. These events provide clues about how sensitive the system can be, though the modern world has different boundary conditions because greenhouse gases, ice sheets, and global temperatures differ from the past. Paleoclimate records come from ice cores, marine sediments, fossil shells, chemical signatures, and other archives. They show that the climate system has not always changed smoothly. Ocean circulation can reorganize and regional climates can respond sharply. This history is one reason scientists take the risk of a weakened Atlantic circulation seriously. The past is not a direct script for the future. It is a warning that the ocean has gears the surface world rarely notices. When those gears shift, the atmosphere follows. Human civilization developed during a relatively stable climate interval. A major disruption to Atlantic circulation would test systems built around that stability. Monitoring this hidden circulation requires international scientific effort. Mooring arrays measure currents, temperature, and salinity across sections of the Atlantic. Argo floats drift through the ocean and profile temperature and salinity. Satellites measure sea surface height, winds, temperature, and gravity-related features. Ships collect direct observations. Models combine physics with data to simulate how the system behaves and how it might change. No single instrument can see the whole circulation. The system is too large and too deep. Scientists must assemble a picture from many sources, each with strengths and limits. Direct observations provide detail but cover a limited time. Paleoclimate records extend far into the past but require interpretation. Models explore futures but depend on assumptions and resolution. This is one reason public discussions can sound uncertain. The uncertainty is not ignorance. It is the result of studying a system that moves through an entire ocean basin and changes across decades. The more carefully scientists look, the more precisely they can describe the risk. Yet precision does not remove urgency. This Atlantic engine matters because the human world is built around climate patterns it did not design. Cities, ports, farms, fisheries, energy systems, insurance models, and national food supplies all depend on assumptions about weather and sea level. A circulation shift would not affect only remote scientific graphs. It would enter crop yields, storm risk, heating demand, coastal planning, shipping routes, and migration pressure. This is the unsettling truth of ocean currents. They are quiet until they change. A hurricane is visible. A flood is visible. A current system can weaken beneath the surface for years before its broader effects become impossible to ignore. It works through averages, seasons, basins, and probabilities. Its danger is distributed across time. The current that could change the world is therefore not dramatic in the usual sense. It has no face, no breaking crest, no single day of arrival. It is a slow-moving structure of planetary balance. If it weakens enough, the consequences would be felt as weather, water, food, coastlines, ecosystems, and politics. The Atlantic circulation has moved through human history without asking to be noticed. It carried heat while empires rose, cities grew, ships crossed the ocean, and industrial civilization filled the atmosphere with greenhouse gases. Now it has become one of the clearest reminders that the ocean is not passive. It is part of the machinery that makes the modern world possible. The fear surrounding this Atlantic circulation should be handled with care. Panic is not understanding. Simple apocalypse stories flatten the science. Yet complacency is equally dangerous. The circulation is real, the vulnerability is real, and the consequences of severe weakening would be large. The responsible response is attention, measurement, emission reduction, adaptation planning, and respect for uncertainty. A current hidden beneath the Atlantic could change the world because the world is already connected to it. The warmth of a winter, the height of a coast, the path of rain, the strength of an ecosystem, and the stability of food systems can all depend on water moving through darkness. The ocean's greatest powers are often invisible from shore. That is why they matter.